When autonomous drones or rescue vehicles plunge into thick smoke, the advanced machine vision algorithms guiding them completely go blind. The culprit is what optical engineers call scattering media, elements like fog, heavy smoke, or underwater turbulence that physically scatter light before it can reach a camera lens. In life-or-death scenarios like fire disaster and rescue operations, this visual degradation is fatal. Take a look at this photograph. The intense, non-uniform smoke violently scatters the light, almost completely obscuring the rescue worker in the frame. The standard industry response is to insert an image signal processing, or ISP, algorithm as a middleman. The goal is to computationally clean and dehaze the image so that object detection models can read it. But if that pre-processing layer isn't mathematically precise, even the most advanced downstream AI models are rendered practically useless in a real-world emergency. To build that pre-processing layer, almost all conventional dehazing methods rely on a foundational physics equation called the atmosphere scattering model. It breaks an image down into two distinct parts: the direct transmission of light from the object and the environmental illumination, the scattered light itself. But solving this equation for a clear image creates what mathematicians call an inverse problem. To isolate the clear image, you have to solve for this unknown variable, t of x. This represents the transmission map, effectively the physical depth of the objects in the scene. Current approaches, like the dark channel prior or color attenuation prior, try to calculate this depth by searching the spatial domain. They analyze physical clusters of pixels in the 2D image, looking for dark colors or low saturation to guess how far away an object is. This creates an immediate problem. These methods rely on rigid statistical assumptions. If the camera points at a bright object or a clear sky, the expected dark pixels aren't there, and the depth estimation breaks down. Treating image dehazing purely as a spatial depth problem is a mathematical trap. It forces algorithms to rely on fragile guesses that completely fail the moment environmental conditions become unpredictable or chaotic. Some engineers tried to bypass the atmosphere scattering model entirely with an alternative called peplography. But even this method falls back on spatial probability, using a Gaussian distribution to estimate the scattered media. To reconstruct the image, peplography uses a photon counting detection model based on a Poisson distribution. It essentially tries to calculate the probability of where the clear ballistic photons should actually be. In dense, non-uniform smoke or fog, the spatial variance is extreme. That variance causes massive probability errors in the photon counting model. We see the direct result of this statistical failure on a real dataset. The mathematical breakdown generates severe multicolored noise across the entire subject. These artifacts destroy structural data and edge contrast, meaning a machine vision system cannot identify the rescue worker's boundaries. Even other standard methods, like the dark channel prior, suffer similar fates, often generating thick block and halo artifacts around edges. The spatial methods struggle to maintain integrity when faced with complex scatter. Spatial domain probability models will always generate destructive noise when extreme, non-uniform environments violate their underlying physical assumptions. To solve this, we have to stop looking at an image as an arrangement of flat pixels and start treating light exactly like a transmitted waveform. Optical light traveling through smoke mirrors radio frequency signals fading across a city. The direct wireless line of sight signal is equivalent to unscattered light reaching the lens intact. The delayed, bounced, non-line of sight waves map directly to the light scattered by smoke or fog. Wireless systems already possess highly mature, mathematically proven fading models, specifically the Raytheon and Rayleigh models, built expressly to isolate and calculate signal power from these exact types of interference. By treating image degradation as a signal fading problem rather than a spatial depth problem, we can apply decades of refined radio frequency mathematics to optical processing. To apply these theories to optics, we must move the image out of the spatial domain entirely. We do this using a 2D Fourier transform. This shifts the data into the spatial frequency domain. We are no longer looking at the physical location of pixels. Instead, we are mapping the rate of change in pixel values across the entire image. In this spectrum, rapid rates of change represent the high-frequency data. These are the sharp edges, structural details, and object boundaries. Conversely, slow rates of change represent the low-frequency data. These are the smooth, gradual transitions in an image, like a vast sky or a blank wall. And here is the critical observation that makes this new theory work. Scattering media, the thick haze and smoke, is overwhelmingly concentrated right here as a massive cluster in the low-frequency spectrum. Instead of guessing the depth of individual pixels in the spatial domain, we have neatly and mathematically isolated the scattered signal as a distinct cluster in the frequency domain. The Fourier domain exposes the scattering effect as a filterable frequency band, bypassing the need for error-prone depth maps entirely. This brings us to a specific algorithm built to target this isolated scatter: adaptive removal via mask for scatter, or ARMS. ARMS adapts wireless fading models by treating the low-frequency cluster as the interfering multipath signal. By calculating the expected power of this noise, the algorithm determines the specific amplitude reduction needed to dampen the scatter without touching the rest of the image. It acts as an adaptive Fourier mask directly over the frequency spectrum, reducing the scatter's amplitude. Because the mask targets only the low-frequency cluster, the high-frequency structural edges on the perimeter remain completely active. The raw data integrity is preserved. This approach creates a significant computational advantage. Applying this single mathematical mask requires vastly fewer processing resources than running pixel-by-pixel spatial estimation or powering heavy deep learning models. The final step in the pipeline is running an inverse Fourier transform. This pushes the cleaned frequency spectrum back into a visible spatial image. ARMS mathematically extracts environmental scatter with surgical precision, avoiding the probabilistic noise generated by prior-based methods. When we bring this back to the initial high-stakes scenario of fire disaster and rescue operation, the practical results are clear. If you compare the visual failure of the peplography method with the output of the ARMS method in the exact same environment, the difference is undeniable. Because ARMS preserves the high-frequency data, it immediately restores contrast and structural edge information without warping the underlying colors. This means that downstream applications, like YOLO object detection, can successfully lock onto subjects from the ARMS output. This can be done without requiring expensive machine learning retraining. Shifting image pre-processing to the spatial frequency domain provides the stability required for machine vision in disaster scenarios. But there is one final flaw with conventional spatial methods. What happens to the algorithm when you feed it a completely clear, sunny image? Prior-based methods will often hunt for scatter that isn't actually there. They try to correct a problem that doesn't exist, oversaturating and distorting perfectly clear images, making the algorithm itself a liability. ARMS behaves differently. If there is no dense, low-frequency scatter present in the spectrum, the Fourier mask simply passes the clear data through unchanged. This allows for an always-on system. It operates as a preprocessor that requires no manual toggles and no algorithmic decision trees to adjust for changing weather conditions. By abandoning the depth estimation trap and treating light as a wireless signal, ARMS delivers a computationally light, universally applicable foundation that protects both human and machine perception in any environment.